And welcome back to Chapter 2, which we will be covering Enhanced Interior Gateway Routing Protocol. This is the first of 3 parts. So we'll be looking at the fundamentals of the protocol in this presentation. So this is a distance vector protocol, and we used to teach this in CCNA, which is now only OSPF being taught as a protocol. So what is distance vector? We basically count the number of devices in the direction that we travel. Each device that handles, in other words, each router, adds 1 to the distance, and you would have a limit on the number of hops you could have. So RIP is the original one, and you basically could travel 15 devices away. And with EIGRP, that goes up to 255, so basically does away with the hop limit. The benefit of this is it supports variable length subnetting, and you're able to adjust the balance for load balancing so that it doesn't have to be precisely equal. So most times when you do load balancing in protocols, they have to be equal cost. With EIGRP, you can do unequal, which means you can do a variance of the best cost. So this allows you to send 2 packets down the primary and 1 down the secondary, that sort of thing. The algorithm that is used is dual, which is diffusing update algorithm, which pre-calculates a loop-free path and provides fast convergence for the protocol. So what's made up this protocol? Well, we use a system of protocol dependent modules, PDMs, that allows EIGRP to be modified to suit the protocol being transported. So at the moment it's IPv4 and v6, but you could rewrite a new PDM to support another protocol in the future. So what are the criteria that set EIGRP apart? Well, for administration purposes, we can only communicate with other devices within our own autonomous system. And an autonomous system is devices that are under common administration. So this allows the routers to calculate information based on the same metric standards and exchange their routes with each other within that autonomous system. So what is the metric? Well, for all intents and purposes, out of the box, it's basically bandwidth and delay. So there are multiple elements that can be taken into effect for the calculation, but the 2 that are on by default are bandwidth and delay. We'll talk about the K values, which are the various weights that are used to calculate the metric, in a few slides. So when you look at this diagram here, you'll see these numbers in little brackets. These are the cost of that link So for you that are coming up through the current CCNA, you're used to OSPF, and the metric is cost. So think of this as the cost. All right, it's EIGRP's metric. So based on a calculation, it comes up with a value, and then you add the values together to get your best path going through. So our successor route is 256 plus 256 gets us to router 4, and the backup or feasible successor is our top one, which is 2560. Now there's rules about how this is possible, what triggers it, so we'll go through all of those in a minute. Alright, so successor route is our primary path, so it's the lowest path metric to the destination. Our successor is our next hop router, so the next device that we go through. Feasible distance is our calculated cost, and when we look at the paths from the previous slide, we add those together to come up with a feasible distance to the destination. Next is reported distance. This is the distance that our neighbour is reporting for the metric. And then you have the feasibility condition. This is the rule for determining that backup route. So the reported distance received for the route must be less than the feasible distance calculated locally. So this guarantees a loop-free path, because if the reported distance is higher than the feasible distance that was calculated lower, chances are you're actually going through this local, okay? And as I said earlier, the feasible successor is the backup route. So this satisfies the feasibility conditions. So it's going to be a loop-free alternative. Now, EIGRP uses a slightly different approach to its calculations. So it keeps a separate topology table. So this one you'll be familiar with OSPF, keeping its own various tables to calculate its pathing. Same thing occurs within EIGRP. So it gathers all of its information into a topology table, and then these are the ones that have the dual algorithm run over it to calculate the best pathing. So what makes up the table? The network prefix, the neighbours that advertise that prefix, the metrics that are reported to it. So that's both the distance and hop count, and then the metric calculation, so the load, reliability, the delay, and bandwidth. Now, when we look at the delay, it's the total delay, and the bandwidth is the lowest or the minimum bandwidth along the path. you can use the show IP EIGRP topology command to actually look at the top 2 routes. So this is the successor and feasible successor routes. The optional all links keyword at the end would actually show you the entire topology. So these are your best 2 routes to the destination if they exist. So how do we read it? So on the bottom one here, the path to 10440 has 1 successor, and the feasible distance is 3328. And then we come down to the actual routes. So the successor route is via 10.13.13, and the path there, so there's our 3328, which is the metric, and then the next value in the brackets is the reported distance from our neighbour, which is connected via gigabit Ethernet 01. Our feasible successor, next best route, is via this device, and as you can see, the metric is higher than the primary at 5376, and the reported distance is 2816. So you can see there that the reported distance is below our calculated distance. Okay, so there's our feasibility condition, that the reported distance is lower than our calculated distance. Now, when we are doing our convergence, we get all the network connections sent to us. So this enables the local device to form its own topology. Alright, and it doesn't have a timed advertisement like RIP and OSPF. It exchanges all of their routing information with everyone within the domain, and it will receive incremental updates when changes within the topology occur. So it's very important that the protocol keep track of its neighbors so that it can send updates when changes occur. So it does this via messaging, which is 5 types of packets that are used to communicate with each other within the domain. Now, EIGRP is protocol number 88 within IP, and it is not a broadcast, it is a multicast protocol. It will use unicast when necessary, but it prefers to use multicast packets. That's its default way of communicating. So routers listen to the multicast group address of 224.0.0.10 and with the MAC address there of 01.0.0.5e zeros and A. So the protocol runs over technologies that support multicast, and when that technology doesn't support multicast traffic, it converts that into unicast traffic and sends it. It doesn't like doing that because obviously unicast means it's got to send multiple packets for the same information, whereas multicast, it just sends one packet out to reach everybody. Excuse me, I got the hiccups. So, what protocol does EIGRP use to communicate with others? Reliable Transport Protocol, RTP. And this enables it to actually have two-way communications with its neighbours. So it gets an acknowledgement of the messages back. So to be able to keep track of this, it uses sequence numbers on each packet. So we should remember back to our TCP handshake, where sequence numbers and acknowledgements are used, and it's based on that sort of conditions. So what are the 5 packet types? Well, the primary one there, number 1, is hello. This is the protocol message type that discovers our neighbours and keeps track of whether the neighbour's still available or not. So this is our constant messaging that is sent out to monitor our neighbours. Then we have request, update, query and replies. So you send a request to get specific information from your neighbours. The update is the change of status. Query is where we want to get information during convergence. Now, convergence is when we're initially starting up and we're waiting for everybody to have the same topology information as everybody else within the domain. And replies are our response to the queries. So within the process of getting our neighbours acknowledged and found, we're sending the hello packets out once we enable the routing protocol. And it's forming its routing information base, which is the information that it's being shared from the other devices. So sends out the hellos, then it enters a initialization state, which it gets an acknowledgement, then it sends the routes that it knows to its neighbour, gets the acknowledgement, then sends an update of the end. So it's basically sending all of its information to its neighbour, and the neighbour is doing the repeat to itself. Now, what does it need to match before exchanging this? So the K values, in other words, what parts of the formula for the metric calculation are going to be used. So by default, this is our delay and bandwidth values. So if a router is using one of the others, like reliability, they're not calculating the same metrics, so they're not going to share information. The primary network or subnet need to match. They have to be part of the same autonomous system. And EIGRP has authentication parameters. In other words, you can challenge your neighbours to make sure they're an authorized device to exchange routing information with. That brings us to the end of our first part, which is the fundamentals of EIGRP. Thank you for joining me, and I'll see you in the next one. Bye for now.